Last one. We're going to use these estimates we've been talking about so we can find those areas, the exact areas, use some limits, make infinitely many rectangles. You know, showed you that. Get better and better and better the more rectangles you make. You know, this next game is going to probably be the challenging thing. Notationally, this is pretty brutal. I'm going to force you to do it because I need you to understand what these summation symbols mean and what is integration, how it all works, ties in, because later you're going to need to know it, and I would rather you be stumbling upon the new concepts than still sitting 10 steps back behind not knowing what the F is going on. So I'm going to make you play these games. I'm going to force you to do this. So you might need to watch this one a couple times or at least watch the mechanics as to how it's going to work. So here we go. We're just calculating the limit of Riemann sums. So what this does is this says, you know, this is what we found. L sub n. We found L7 in our last one. And then you found R7. We're like, well, there it is. But if we make n infinitely many rectangles, that's actually going to be the area. Cool. But let's see how that shit's written. I'd like to maybe change it up just a tad. So I'm gonna zoom on into it and go, wait. We could write this differently. That this, oops, a little thicker. Come on. Okay. It's still the same size. I suck. All right, yeah, there we go. I think I got it now. I think, you know. All right. It's equal to the limit as n goes to infinity, but now let's use a sum symbol. This is equal to, and now we have f of x something. Like, notice the numbers will change. 0 to 1, and then we go to 2, 3, 4, 5. It would continue getting bigger. So we're going to say, let's start our I at 0, and we're going to go up to n. And now we put a sub I here, telling us that on the first one, we'd have f of x 0. After 0 was 1. But, oh, I'm forgetting something. Times that change in x. So look at the index from right down here. That's where we would start our first one. And then after 0 is 1, and then our next term would have had a 2, and then a 3, all the way up to n minus 1. We wouldn't have gone to the last one. And it actually doesn't matter whether you do this with the left or you do it with the right. It turns out to be the same thing due to all the limits. So here it is. Here's our new little game we're going to play around with right here. We're going to use this to approximate, or not to approximate, to actually find the exact area under the curve. And then soon we will see, this will be after 5.1. We could say that this is the same thing as the integral from a to b of f of x dx. If we want to find from the interval from a to b. All right, let's get after it. We won't be messing with that integral yet. So let's see our question. Find the area of the region bounded by the graphs. Oops, I got that shit written again down here. Find the area of the region bounded by the graphs of the function f of x equals x squared. Okay. Let's just kind of draw it up real quick. X squared, oops. Let's go. Something kind of like that. And then, but we just want to look at it from where? From 0 to 3. So right there, so I'm going to call that 3. I guess that height would be 9. So we just want to look at it right here. And above the x-axis. All right, so it's just all this shit in here. You want to find that area. So we're going from 0 to 3. That means that our A is 0. That's where we start. A equals 0 to our B equals 3. A is the start. B is the end point. Cool. We got those. Now, when we used to break it up, like say if we went from 1 and 2, we break it into say 3 pieces, wouldn't we say like our delta x Wouldn't we say our delta x would have been 3 minus 0 over how many pieces? 1, 2, and 3 pieces. And we divide it and be like, oh look, the gap is 1. But now we want to break it into n pieces, so it works for any of them. We're like, well, look at this. Right, because our change in x is b minus a over n, so we just put the b minus the a over the n, and instead of putting in a number for n, just leave that shit alone. We're going to call our change in x 3 over n. And really our game is we're trying to fill this in. Whoop, we already found that one. Now we need to find our f of x sub I. And this is a little bit tricky. What we're going to say here is our x sub I, whichever one it is. Well, let's think about what x0 is, the first one we look at. Isn't this just equal to a? And then our second term, f of x1, well, that would be a plus, and what would it be? I think that would be, wait a second, the gap is, isn't that change in x thing each time? So we actually add a change in x every time we add another one. Huh. But let's write this in. One of them, x2, isn't this a plus? And then wouldn't you move 2 of those change in x's over, or 2 points over? So 2 times your change in x. X3 is a plus 3 times your change in x. Can you start to see a pattern? That if you keep going down, that here you're going to have a plus, all it is n changes in x. But let's see if we could write it for any of them. How about the ice? The ice, something that's right in between, because we need to match up to this index here. I told you this is going to get rough. We need to match up to that index right there. We want to create an f of x sub I. So let's see, we need to create an I somewhere, and where the I is, well, look, here's the 0th term with 0 times your change in x. Here's the first term with 1 times your change in x. Here's the second term, 2 times your change in x. The third term. So I'm thinking we could say that our x sub I, whatever that is a plus I times your change in x. And there's that formula we were looking for. Now, I'm doing a problem and building it all at the same time. So there's a ton to sift through here. I'm introducing the topic and I'm doing an example all in the same time. I know this can be a little bit rough. So we're going to go take a thing that we've messed with before. A is equal to the limit as n goes to infinity of our sum from I is equal to 0 up to n. And now we're ready to tackle it, right? So we had to find something for this. Well, we found it, but let's put it into specifics for ourselves. X sub I is equal, what's our A? Where do we start for ours? Our A was equal, where is that? A is equal to, oh, it's equal to 0. Well, that's good news. 0 is always a good number. Plus I times, and it says times your change in x, right? And our change in, oh shit, the change in x. The change in x. It's just 3 over n. Cool. So we put that times 3 over n. Let's clean it up, and we're like, I think our x sub I is equal to, 3i over n. There it is. Now we got it. Now we cleaned it up. So let's put that in, but we put it inside of our function. Oh, you thought it was done. No. So we got our 3i over n we pop in. Now we got to put in our change in x. Well, that's not that big of a deal. Our change in x, wasn't that from right here? That was equal to 3 over n. We're almost there. We have our function, but what the hell was our function? In order for us to solve this, we need to know what our function is. What did we start with? Our function is x squared. So it's saying we need to take our inputs inside of here and square them. Right? F of 2 would be 2 squared. So we need to take that out and figure out what we got. Okay, here we go. Sorry about that. The limit as n goes to infinity. The sum, I is equal to 0 up to n. And now we're going to say that f was just something squared. It's just something squared. And it's what's inside. It's the 3i n squared. Now we're going to use all those sum formulas I gave you back in those little review videos. All right? Let's go in and now we can tackle this problem. We'll do the limit at the very end. And right now we're just going to break this up, rewriting in our summation. We'll square that and we'll see what do we end up with. I think we're going to end up with 9i squared over n squared times that 3 over n. Well, do you know what actually doesn't have anything to do with this problem? With the sum, the only thing that actually matters in our sum is actually going to be that I. So the ends don't matter all that much. We can get them out. We want to take these and the numbers, and we want to get that shit to the outside. And we want to leave just the I squared back behind. All right, whatever that nonsense is that isn't I, get it out to the front, get it away from this, and we'll start to see why we want that. So up in that numerator, we have 9 times 3. So again, I'm going to write all this stuff out. I know it can become super tedious, but we're going to put outside of this. So we have our 9 times our 3, all right? So that's 27. We yank that out to the front. And now we have our n squared times our n. That's n cubed. So why don't we yank that out to the front too? Actually, let's change the color on that. I'll leave that in blue. Just say that's what we yanked out, and then what's left behind was just the I squared. Well, we have a formula for what I squared is. Let's go right through. This is equal to the limit as n goes to infinity of 27 over n squared. And now we're just going to replace right inside here with what this equals. Of I squared. Well, come on, get out of here. This thing is just going to be equal to n times n plus 1 times 2n plus 1 all over 6. So that's what we're going to replace it in there with. Cool. Now that we have it, let's clean it all up and see what we have. And now, oh, look at that. We're doing a freaking limit problem. Oh, shit. So let's get the 27 and the 6 out to the front. We'll reduce that in a second. What do we got here? When you expand all this out, geez, I don't even know what all this stuff is. So that's going to be an n squared plus n times our 2n plus 1 all over n squared. Isn't that what we got down here? Is there some sort of n squared? I feel like I'm missing an n. Where did my n? There it is. It's from back. Why didn't you tell me? Oh, yeah, because I can't hear you. It's an n cubed. That was an n cubed the whole way down. I bet some of y'all have been screaming, ah, it's a cube. Well, I caught it eventually. I knew it because it has to have the same sort of top and bottom as we mess with this. And now we can show you the little bit of the trick. When we bring this together, the only terms I really give a shit about is the first one. That's going to become 2n cubed plus, and then we have some other shit that we really don't care. It's going to end up becoming 3n squared plus n. All over our n cubed. But now that since we've gotten through our limits, since we've gotten to this point, okay, I got to reduce this shit down. That's another 9 over 2. Outside the limit. Now that we've done this, you paid your dues with the limits. I'll let you do this piece here. I'll let you do this. When you see, just look, 2n cubed and n cubed. Everything else doesn't even freaking matter. None of that shit matters. What's 2n cubed over 2n cubed? It's just 2. The answer is freaking 2. So you get 9 halves times 2, which is just equal to 9. That area underneath that curve from 0 to 3 for x squared Had an area of 9. Oh my gosh, look at all those steps. Look at all of that work. And you get to reproduce it. Man, oh man, I'll keep it pretty straightforward. I won't make it too terrible on you, but you're going to have to play this game. So you might have to watch through this thing a few times. Just watch the mechanics. All right? Don't skip over this shit.